Welcome to AP Podcast 8.9 and beyond. What we're going to do is look at the electron model for molecules, and it's going to encompass three parts: the valence electrons using Lewis dot structures, and Vesper theory, and then looking at the types of orbitals. And for my students, these two things are all review. So when we think about molecules bonding, we've got this situation that we already know. They're going to share their electrons, and we've got some models on how to kind of show those. The first one is a Lewis dot structure. And again, we've done Lewis dot structures, so I'm just going to go over these quickly. If this is the first time for you, sorry about that, but we'll definitely help you in class if it happens. But basically all Lewis dot structures do is show you where the valence electrons are. And for most purposes, it's going to be 8 electrons for each atom. That's an octet. Or for hydrogen, it's going to be a duet. But let's say, for example, I want to show the valence electrons of carbon. Well, carbon has 4 valence electrons. I would put 4 dots like that. And so when I'm going to bond, that's where it's going to work out with the dots. Now, if we want to show a bonding pair, let's say I'm going to have this carbon bond to a hydrogen, all right? Here would be a pair of electrons in between. So this right here is known as a bonding pair. And when you have 2 electrons in between 2 atoms, that's considered a bond. So some of the rules is there's a number of ways of doing this. Some of my students like to add up all the valence electrons and make sure you have that many. Some students like to just make sure that they have the right number of valence electrons for each electron. It really kind of depends on how you want to do it. Again, you've got to make sure that that octet rule is satisfied for all elements, of course, except for H. And then as far as where the electrons come, let's say you're trying to make it work out, and that means when we have double bonds and triple bonds, sometimes you have to just move electrons around. We're not going to really worry about where they come from. A number of you will get the joy of that experience when you take organic chemistry in college. But we're not going to worry about that right now. And then one last thing, and you'll see this happen quite a bit. Sometimes we'll just draw a line representing a pair. So if you see that, that's the same as 2 electrons. All right? So let's try a couple. And I'm just going to start out with this first one. And typically when we do these, we put the element that's first, we put that in the center. All right. Now, if you don't really know, because sometimes it's it's a compound you've never seen, and there's 2 things in the front, well, it really goes to the element with the lowest electronegativity. But that's not something we usually have to worry about with. So here's phosphorus in the middle, and phosphorus, if you looked on the periodic table, has 5 valence electrons. So I've drawn the 5 valence electrons, and now I'm going to bring in an oxygen with its 6 valence electrons. So 1, 2, 3, 4, 5, 6. Okay, so there's 6. Now notice there's 8 around oxygen, so that's pretty content. And then I'm going to bring in a chlorine. I'm going to bring 3 chlorines in. And chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Boy, that doesn't show very well. Let me try blue. 1, 2, 3, 4, 5, 6, 7. All right. Okay, so there we go. So if you look around every atom, they all have 8 electrons, and that's satisfying the octet rule. And that's really all you have to do to draw a Lewis dot structure. Let's do sulfate. All right, we've got sulfur with its 6. 1, 2, 3, 4, 5, 6. All right, and here comes one oxygen with its 6 valence electrons. Here comes another oxygen with its 6 valence electrons. Here comes another oxygen. I'm going to make the first valence electron make the bond. 1, 2, 3, 4, 5, 6. Oops. Okay, and then here comes this one. 1, 2, 3, 4, 5, 6. Now you'll notice that this oxygen, this sulfur, and this oxygen all have an octet, which is good. However, there's only 7 electrons right here, and there's 7 electrons there. Well, that's why sulfate gets a -2 charge, because you're going to get a couple bonus electrons. I'll just make a little X. There's one bonus electron, and there's a bonus electron. So now every element has an octet, which is a good thing. So that's just a simple review of that. let's talk about something that we did not talk about last year, and that are the exceptions to the octet. It turns out that boron will sometimes have 6 electrons around it, and in the AP chemistry curriculum, boron trihydride or boron tetrafluoride, that's the one that's used over and over and over. So I don't want you to be shocked when you see something like that and they want you to draw the Lewis dot structure. It would just simply be something like this. B, you'd put an H, an H, and an H. Okay? And that would be perfectly fine because boron is only going to get 6 electrons. Now, sulfur, on the other hand, we know this compound forms. Sulfur hexafluoride, and it's actually a really cool compound because it causes your voice to be really, really deep if you inhale it like hydrogen. And I'll show you that video. But anyways, it turns out that sulfur has 12 electrons, and obviously 12 electrons is much more than an octet. So what is going on here? Because we know that SF6 happens, and so the idea of what is happening is that the S's and the P's are filled, and the 3S and the 3P. However, sulfur does have some 3d orbitals available, and that's where those extra electrons go. So let me draw a couple so you can see what I mean. Here we go. So let's go chlorine trifluoride. So we'll put chlorine in the middle with its 7 valence electrons. Okay. And then here comes a fluorine. I'm going to draw it right here because that all makes sense to us, right? If we were going to draw CF, that's what we come up with. But we know there are 2 more fluorines on this. So I'm just going to put 1 here. And I'm going to put 6 around the fluorine. Okay, and I've got this 1 electron. Well, I want that. I've got this 1 electron over here. I'm just going to leave it right there. Okay, and then I'm going to bring in another fluorine. 1, 2, 3, 4, 5, 6. And here's that other extra electron. Now it's a pair of electrons. Where are those pair of electrons going to go? Well, they're going to go on the central atom. So we'll just stick them right here. All right. You could really stick them in any corner. But the bottom line is it has to be on the center atom. So let's do xenon tetrafluoride because that's another compound that we know that truly does form, and so we've got to have a way of drawing it. So I'll put xenon in the middle. Now you're going, wait, that's a noble gas. It shouldn't react. Well, it turns out that you can, under certain conditions, make this compound. So there's xenon with its octet. It's perfectly content, right? Well, let's bring in a fluorine. 1, 2, 3, 4, 5, 6. I'll put the bonus 1 over here. Another fluorine. 1, 2, 3, 4, 5, 6. I'll put that bonus over there. Bonus over here. Bonus over here. Now, each fluorine has an octet, which is great. So what am I going to do with these 2 pair of electrons? I'm going to stick them on the central atom. If I could show this in 3 dimensions, imagine these 2 dots going in and out of the screen. Okay, one's going back and one's going up. But there you go. So there's 6 pair on that central atom. All right, so that occurs with some elements. Now, here are the kind of the rules we need to follow with exceptions to the octet. The second row, these elements right here, they always observe the octet rule. Okay, and then it turns out boron mostly, and sometimes beryllium, will have fewer than 8, so they don't have an octet. And then the third row and heavier elements, so that's anything beyond the third row, can have more than 8 electrons on the central atom because they have these empty d orbitals. And this is important because sometimes that question pops up. How in the world can these elements exceed the octet? And the answer is they have empty valence d orbitals to accept those electrons. Right? So when we just do this as a rule, we want to take care of the octet rule first, and then if we have those extra ones, we put those around the central atom. All right, we're almost done. Last thing, resonance. Every once in a while you'll have a compound that has more than one structure. It's always something that has a double bond. For example, if I were to draw nitrate, and I'm going to not draw all the valence electrons just to save time, it looks like this. Okay, But the problem is a Lewis dot structure cannot represent what truly is going on. Because is the double bond there? Well, couldn't I have just drawn it there? Or couldn't I have just drawn it there? Well, when scientists look at the bond length of an NO bond, it turns out it's got a value that's in between a single bond and a double bond. And you've got to remember, this is a model that helps us understand chemistry, but really what's going on is electrons are moving around, and so it doesn't quite fit our perfect model. It's not like the double bond is moving between each element. In reality, it's a shared thing. So if you want to say, well, each bond has a value of 1.3, that's like 1 1/3, that's okay. But you have to understand that we can't, one of the shortcomings of the Lewis dot structure is we can't represent all the symbols. So what we would do is we typically draw a double arrow and we draw the structure, and we draw another double arrow and we draw the structure. And so you've represented all the possible choices, and there's a double arrow going in between. So that's really what's going on. And then last but not least, this may never pop up, but it's kind of interesting. If I were to ask you to draw the electron, or pardon me, not the electron, the Lewis dot structure for NO2, you go like this. There's nitrogen with its 5 valence electrons. Here comes an oxygen with its 6, right? Here comes another oxygen, 1, 2, 3, 4, 5, 6, and I would just take this one out of here and I would put it over there, and now we have some problems. One, we're going to need a double bond, but no matter what we do, look at this. We have an odd number of electrons, and for AP it only happens with nitrogen, and oftentimes it's never even brought up. But that is, again, another shortcoming of the Lewis dot structure. It doesn't deal with those odd numbers. So we really don't worry about it. But just kind of a side note. All right, so we'll practice Lewis dot structures tomorrow and see how it goes. And we'll draw some resonance structures and expand some octets. And I'll show you some cool shapes. So see you next time.